Welcome to CET3136C. This is Professor Evans, and this is the Logic Devices Programming course at Valencia College. I'm going to begin this course with our first lecture, which covers chapter 1 of the textbook, Digital Design using VHDL and PLDs. So the objectives for this video are that you will be able to describe the advantages of PLDs, describe the VHDL design methodology, summarize the VHDL design flow, design a combinational logic circuit on the Max-10 board using the Quartus Prime 18.1 software, and produce a functional simulation of a VHDL architecture. So in a nutshell, with this video, I'm going to introduce you to some basic concepts behind VHDL, and we're going to work on our first lab today, where you will write some code and program it onto your Max-10 PLD, so that you can see how it actually works. So to begin, VHDL is a programming language for designing and modeling hardware systems. VHDL is short for Very High-Speed Integrated Circuit Hardware Description Language. And if you think back to your Digital Systems 1 and Digital Systems 2 courses, you built a number of circuits on the breadboard using an IC and wires and switches for inputs and LEDs for outputs. Well, this course is going to take some of those exact same circuits and teach you how to write a description for those circuits using VHDL, which basically means you're going to learn how to convert the ICs and the wires that you used in Digital Systems 1 and Digital Systems 2 into code. And then we're going to program that code onto a circuit board that is able to be programmed. And then that circuit board will run your code, and it will behave in the same way as the circuits that you built in Digital 1 and Digital 2. So that's sort of the overarching point of this entire course, is to learn how to take some of the digital devices you already know how to build and learn how to write them in VHDL. So a PLD stands for a programmable logic device. It's an electronic component used to build reconfigurable digital circuits. So if you think about your typical circuits from Digital 1 and Digital 2, you use different ICs, which are integrated circuits that consisted of logic gates and had a fixed function. For example, an AND gate can only do one thing: follow the truth table for the logic idea of AND. Each one of your ICs was hardwired to only do one function. Well, a programmable logic device has an undefined function when it is created. And that means you can program it to act how you want it to act based on the code that you use. So a PLD is a circuit that must be programmed using a specialized computer software. In our class, we're going to be using the Quartus Prime 18.1 software to program our PLDs. So in this class, you will be using the Max-10 PLD, and you'll be able to connect it to your computer. You'll be able to program it through your computer, and then you'll be able to manipulate the switches or the push buttons on that circuit board, and you'll be able to see LEDs or hex displays turn on, turn off, depending on the function of the program that you're writing. So the PLDs will be supplied by the lab, and you will be able to use VHDL to program them. So in summary, PLDs are pre-manufactured integrated circuits that can be programmed to perform logic functions, and then they are reprogrammable. So each time you program something to our Max-10 board, that board will execute your code as long as it has power. Once you disconnect the power, your code will be gone, and you'll have to reprogram it each time you connect your circuit board to power once again. Some of the advantages of a PLD: they're often smaller in size because of the fact that they have fewer chips. The cost is smaller because you have reduced chipset. There's a quicker turnaround time for manufacturing samples. And in my opinion, the best advantage of a PLD is changes are made easily without having to change an entire board layout. Imagine trying to wire a particular circuit using the ICs you used in Digital 2 and then changing the function of that circuit slightly, but that might cause a massive amount of rewiring. With a PLD, a small change in logic could be a very small change in code, and then you can just reprogram your PLD with that upgraded circuit. So changes are easily made without having to change the entire board layout of a particular circuit. And then with PLDs, a company can create proprietary hardware with custom PLDs for a specific function. So when we talk about VHDL, there is a design methodology that is used to create the code you're going to run on your PLD. VHDL is used to describe both the system being designed and the test bench used to verify the design. So the test bench is a secondary piece of code that's going to verify that your first piece of code works the way it should. We're going to learn how to write both a VHDL design as well as a complementary test bench during the course of this semester. So a software simulator tool is often used to simulate your design to verify its functionality and its timing. So today we are going to do the first lab, and we are going to simulate the code that we're going to write before we actually program it onto the PLD. That's called a functional simulation. That simulation is going to help us ensure that our code works the way it is intended before we actually program the PLD. The design methodology for VHDL also uses a software synthesis tool to create the logic described by the VHDL description. So we're going to be typing VHDL code into Quartus, and that software is going to perform synthesis, which is going to take our code and transform it into the logic that needs to be programmed onto the circuit board in order for that PLD to execute the code or to execute the function that we're trying to program. Quartus also is a software with a place and route tool to map the synthesized logic to the target PLD and to generate a timing model and a configuration file. So Quartus is our software that's going to be sort of the medium between our VHDL code and the PLD itself. And that software is going to include things like the place and route tool that basically connects the logic to the actual hardware on the PLD. So we also have to have a physical PLD to implement our design. So part of writing code in VHDL is to have a PLD to program it on. Many high-level software programs may only require you to be able to execute Java itself, on a computer, for example. Well, VHDL, the point of VHDL is that it's supposed to be programmed onto a piece of hardware. So we do have to have that piece of hardware, which is our PLD. And then the design methodology also uses information in the configuration file. That configuration file is generated by Quartus when we compile everything. And that's what's going to be used to physically program the PLD. And you're going to see all of these steps through this lecture to write the code and to get the configuration file needed to actually program the PLD. So VHDL is the primary language of this course. However, there's a similar language to VHDL called Verilog. They're both industry standard hardware description languages. So if you go into industry and you go into hardware design, you will notice that some companies use VHDL and some use Verilog. They're quite similar. They're both used to describe the hardware logic for PLDs. VHDL is based on Ada, while Verilog is based on C. And VHDL contains more constructs for high-level modeling. And basically, it just comes down to the type of design you're implementing and what you're trying to do. Both of these languages are very powerful, both of these languages are very common, but at the end of the day, VHDL is considered a bit more high level. And so that's why we're going to focus on VHDL in this class. So a VHDL model is a textual description of a system that, when simulated, behaves like the intended or actual system. So think about, for example, the XOR gate that you've used in previous classes. We know that we can get the IC to implement the idea of XOR. Another way to do that is to write a program for it. In VHDL, your model is your program that's going to behave like that XOR gate when you simulate it or when you program it onto a PLD. So essentially, your VHDL model is a text file, and it has to contain two pieces of information: an entity part that describes the inputs and the outputs to your system, and then an architecture part that describes the functionality. So with every design that we make in this class, you will have to have an entity and an architecture. Again, the entity describes the inputs and the outputs. So for an XOR gate, I have 2 inputs and 1 output. And then the architecture describes the functionality. So within the architecture, I'm going to implement the Boolean logic behind the idea of XOR. And that text file is going to be created in Quartus, and then the software Quartus is going to take all of that code that we've written and generate the necessary files needed in order to program our PLD so that it can behave exactly like an XOR gate. So in digital systems, logic signals transfer information from one component to another and from one system to another. A change in a signal's value is called an event. For example, you've often studied what happens to a counter on the positive or negative transition of the clock signal. That transition is an event. So anytime a change from 0 to 1 or 1 to 0 happens, we call that an event on a signal. And one key feature of a hardware description language is its ability to describe events that occur simultaneously. So if you've ever written code for any other course, what you'll see, or what you know to be true, is that your code executes sequentially from top to bottom, one line at a time. In a hardware description language, you can have pieces of code that run at the same exact time. The same way that 2 signals in a circuit from digital 1 or digital 2 can change at the exact same time and have an effect on the output. So simultaneous events are intrinsic to any digital system operation, and we call these concurrent events. So within our VHDL code, we're going to have lines of code that run concurrently. One doesn't happen before the other, even though if you look at the program from top down, you'll read lines one after the other, but the program itself will execute certain pieces of code or certain lines that you write at the exact same time. So that's something to keep in mind that's different from some of the other languages you've probably encountered. Whenever we design an architecture within VHDL, there is a design flow that's typically used, and that flow is shown on the screen. Before we start our design, we look at the requirements. And based on the requirements, based on what the code or based on what the project is requiring us to do, we develop a specification. And from that specification, you start to write your VHDL design description. That's basically writing your text file with that entity and that architecture that explain the inputs, the outputs, and then how the system is supposed to behave. Once you write your description, you'll compile that design and you'll develop a verification plan, which means how can I ensure that the code I wrote works as it's supposed to? How can I test it and ensure that it's going to work correctly once I program it on the PLD? And that's where the test bench comes in. You'll write a test bench that will verify your code to be correct. So before we ever program our code, we'll compile it and then figure out how to test it using a test bench. Once you write the test bench, you'll compile the test bench and then you'll do a functional simulation. That simulation is where you simulate your code using a program like Quartus to ensure that your code works the way it is intended before you actually start to program that code onto your PLD. So once you have passed the functional simulation stage and you're sure your code works the way it is supposed to, then you'll select the PLD you're going to program, and then you'll begin the final steps that you'll see here, which all occur within Quartus. Quartus is the program that will synthesize your logic, you can do a post-synthesis simulation, and then you'll have the place and route logic to PLD. You can choose to do a timing simulation at that point, so these simulations are things you can do along the way. But after Quartus has synthesized your logic, Quartus will do the place and route logic to the PLD, and then Quartus will give you a file that you can use to program your PLD. Once you do that, you actually investigate whether your code works on the PLD itself. And that's sort of an overview of the design flow that we're going to use whenever we create an architecture for a PLD. And that's just a quick introduction to VHDL. What I want to focus on today is understanding the entire process, from writing the first piece of code, to compiling it, to functionally simulating it, to actually programming your PLD, and then verifying that your code works on your PLD. So right now we're actually going to begin Laboratory Exercise 1, which is called Introduction to VHDL Design and Programming. You'll find this laboratory exercise posted on Canvas. What I'd like you to do is follow along with me using Quartus on your own computer and a Max 10, which is also called a DE10 Lite board. You should make sure you have Quartus and the USB Blaster 2.0 already installed on your computer before continuing, because if you're going to follow along with me, you need Quartus in order to do that. What I want you to do is to follow along with the video and ensure that you can get the same results that you see on the screen. Your first lab report will require you to basically summarize this experiment as shown in this video. After this, all other lab reports will require you to write and test your own code. So with this first video and with this first lab experiment, I'm going to show you all of the steps that you have to take to write a piece of code and program it onto your PLD. After this, you will be expected to do all of these steps on your own, and what's going to change each week is the way you're going to write your code or the methodologies you're going to use to implement your code as we learn about the VHDL language. So, at this time, we're going to start that first lab and get your feet wet as to how this whole process works using your PLD. And here's the problem statement that we're going to investigate for this lab. We have a truth table below. We're going to write the canonical sum of products Boolean equation for each output. And then we're going to write a complete VHDL design description of a design entity that accomplishes the function defined by the truth table. Basically, that means I need to create a piece of code in VHDL that is going to simulate this system with 3 inputs and 2 outputs. And as the inputs change, I need my VHDL program to provide these same exact outputs that you see in this truth table here. And just like in Digital 1 and Digital 2, we used LEDs to verify the output of a circuit. We'll be using LEDs on your PLD as well. Just like in Digital 1 and 2, you use switches to manipulate the inputs of your circuit. There are switches on your PLD. So we're going to be doing the same thing. We're going to be manipulating the switches, and we're going to look for the outputs to match the truth table given. So we're going to design the system that will implement this truth table. If you look at output X, we can write the sum of products equation by looking at the values of A, B, and C whenever X is 1. And that's your sum of products equation for X and your sum of products equation for Y. So basically I know that X will be high based off of these inputs here, this combination of inputs, and Y will be high based off of this combination of inputs. So now that we have our Boolean equation for each output, the goal is to design a VHDL entity that will take 3 inputs, A, B, and C, give me 2 outputs, X and Y. Based on how these 3 inputs change, X and Y should be high as described in this truth table. So that is our goal. And what we're going to do is start by opening up Quartus and begin to type our code. Alright, so I now have Quartus open on the screen. And what we're going to do is walk through every single step you need from start to finish to create a program for your PLD. So we're going to start by going to File, New, and going to the New Project, New Quartus Prime Project right up here. This is the new project wizard. We're going to go ahead and hit Next. And then you're going to select the working directory for your project. This is where all your files for this particular project are going to be stored. Every time you start a new project, you're going to want to have a different location to save all those files. So I'm going to go ahead and select a location. I'm going to create a new folder here called Lab 1. And that's going to be my working directory for all of the files in this project. Then we're going to give our project a name. We're going to call it COMB_FCN. This is the name of our project, just because it's a combinational function. So this is the name of our project. Hit next. We're going to start with an empty project, so hit next. We're not going to add any files to this project at this time. In the future, if you have a project that might reference the same file, you can add that file if you've already had it created right here. But for now, we don't need to add any files, so click next. Next, we're going to add our device. The family should be the Max 10 family. The device should be the Max 10 DA family. And then you're looking for the 10M50 DAF 484C7G device. So as you scroll through, 10M50 DAF 484C7G, that is the name you want to select. If you don't select that exact name, if you mistakenly select a different name, your code will not be programmed correctly to your PLD. You'll get an error. So you have to select the exact device, and that name is written on the box of your PLD. So if you look at the box itself on one of the side panels, it says Max 10 10M50 DAF 484C7G. So you can reference the box at any time, but that's the device you're going to select. So hit next. Alright, so now we're on the EDA Tools Settings tab. Within this tab, we're going to select the simulation dropdown. We're going to say ModelSim-Altera. That's just the name of the tool we're going to be using to eventually perform some simulations. And we're going to say that the format is VHDL because that's the type, the style of code we're going to be writing. So click next. At this point, you've finished setting up your project. Click finish. And your project will be created, so you'll have to wait for a minute while it sets everything up. And now we have a new project. Again, verify that you have the correct device name right there. Then go up here and click New, and you're going to select VHDL File. And within this file, we are going to write our VHDL code. So we're going to start with what's called a context clause. And then we're going to follow that with a library unit. Now you're going to begin every program that you write in this course with the context clause and the library unit. This basically represents a library of functions that we're going to be referencing as we write our code. Without using a library that explains where some of the functions we're using are coming from, your code will not compile. So we're going to start with that library unit and context clause, and then we're going to have what's called our entity declaration. So we're going to start with the word entity. Notice these words are turning blue. That means they're keywords. So you can't use any keyword to be the name of a variable or an architecture. You can't use those keywords for any other name. So anything in blue, notice that is a keyword. So the word entity is a keyword, and that's always going to begin our entity declaration. Remember, the purpose of an entity declaration is to declare the inputs and the outputs to our system. So we're going to call this entity, and we're going to do COMB, no underscore, COMB FCN is. And we're going to write the word port. That's another keyword. Port indicates that we're going to be determining or discussing the inputs and the outputs to our system. So if you look back at the description, we had 3 inputs, A, B, and C. Now with every signal in your port statement, you have to define whether it's an input or an output. These are inputs, so I'm going to write the word in. Then I have to give them a type. We're going to talk more about types later, but for now, when you see that std_logic, that stands for standard logic, and when we declare a signal as type standard logic, what we're saying is that signal is basically going to be a 0 or a 1. That's our only values for that particular signal. So I have 3 signals, A, B, and C. They're going to be inputs to my system. And because of this type here, I know that they're going to be Boolean values, 0 or 1 at any given time. So there's my inputs. I have 2 outputs. So I'm going to give them a name. So my outputs are X and Y, label them as out, and give them a type. They're also standard logic, meaning the output to this system is only ever going to be a 0 or a 1. Notice the syntax here. At the end of my first line, I have a semicolon. But at the end of my very last line, there is no semicolon. Close the parentheses and then semicolon. If you don't have that exactly typed in like this, you will get a compile error. Now, if I had 4 other lines of inputs and outputs in here, each one of those lines right here would end with a semicolon. It's only the very last line in your port statement that does not have a semicolon at the end. So there's my entity declaration, and in order to complete that, I have to say the word end. Just like that. So this right here is your entity declaration. Notice the double dash here gives me text that's in green. That's a comment. So you can add comments by doing a double dash anywhere in your program. Now I'm going to add the architecture body. The architecture body begins with the word architecture, another blue word, so another keyword. We're going to give the architecture a name. I'm going to call it data flow. That will make more sense in the following weeks when we talk about what data flow means. But for now, just consider that to be the name of your architecture. And we're going to say architecture data flow of our entity, right up here, that's where that comes from, is. So this statement here is starting to set up the architecture. It's giving the architecture a name, and it's linking that architecture to a series of inputs and outputs defined by this entity. So we have our entity here, and then the architecture is going to react or respond based on how the entity has defined the inputs and outputs above. So this is the beginning of our architecture body. So once we type that first line, we have to type the word begin, and then we begin writing our logic. So here's where we start thinking, well, how are X and Y determined? How do I know when X is high or when Y is high? That's where that sum of products expression comes in. We're going to take that sum of products expression for X and the sum of products expression for Y, and we're going to turn that into a Boolean expression right here. I'm going to start with this expression right here, X. We have the caret equals. This means gets. X gets. So everything that I write after this sign, everything that I write on the right-hand side of this is going to determine what value signal X will have. Now I'm going to take that sum of products expression for X and type it out. Everywhere you see an overbar, we're going to write the word not. You can hit enter if your line goes outside of the screen in order to keep everything on one screen. So if you go back to that sum of products expression on the first page of the lab, it says that X is equal to not A and not B and C, or not A and B and not C, or A and not B, or A and B and C, or A and not B and not C. And that's what we have written here. So anytime you have an inversion, you can put the word not in front of a signal. Anytime you're using the logic function and, you can just type out and. Anytime you're using the logic function or, you can type out or, and you absolutely want to use parentheses to indicate precedence. So without the parentheses, it would be read left to right with precedence. So the parentheses indicate our groups of things that are in the sum of products expression that you see for x on the first page of the lab exercise. So we're going to follow this idea and do the same for y. So we know that y is not a and not b and not c, or a and not b and c, or I can hit enter here, a and b and not c. So again, make sure you're looking at those sum of products equations and understanding where I'm getting this from. So again, if you look at that paper, y should be not a and not b and not c, or a and not b and c, or a and b and not c. Notice that when I'm done with my Boolean expression, I end it with a semicolon. So remember, x and y are outputs, so I have to assign a value to an output. I'm assigning the value to x by saying x gets, and then x is going to get whatever value comes out of this Boolean expression based on your sum of products Boolean equation. Same thing for y. So these are outputs. Outputs have to be assigned a value. You cannot assign a value to an input. So a, b, and c, these are inputs. They determine what x and y are going to be. So these are my two Boolean equations to describe x and y. When I'm done with the architecture, I need to use the word end, and then whatever I've named it up here, I'm going to end it right there. This completes the code that is going to simulate the problem statement on the first page of the lab. Now we're going to go ahead and save this, and when you save it, you must give it the exact same name as the entity declaration. So go ahead and go to save. It's going to ask you if you want to save it as your project name. Do not save your VHDL code as your project name. There's another file that needs to have the project name. Do not make this file the project name. That's why I gave it something similar, but I took out the underscore. So that is going to match my entity name, and it's going to be a VHDL file, and hit save. And notice at the top of the screen, I have my new name shown. Next, we have to compile this. We have to make sure that there are no syntax errors in our code. For example, if I take out a semicolon right there, I'm going to get an error. So we're going to go to File, Create Update, Symbol Files for current file. And I have changed it because I removed a semicolon, so I'm going to hit yes to save. And down here, you're going to see the status of that particular direction, and you're going to see I got an error on line 13. If I double click that, it'll take me right back to the area where the error was encountered, and because I don't have a semicolon right there, it doesn't know that this line is the beginning of my architecture body. So I'm going to put that semicolon back in. File, create, symbol, files for file. Hit yes to save your changes. And now I have 0 errors, 0 warnings. That's what you want to see when you type your code. If you get any errors or any warnings, you have to stop and fix them. Errors and warnings could be something like forgetting a semicolon, forgetting to name your architecture, or forgetting to use the same name when you begin and end the architecture, forgetting to use the same name when you begin and end your entity, forgetting a parentheses, forgetting your context clause or your library unit. Any of these things can cause you to have an error. So you have to fix those before you continue. Since we have 0 errors and 0 warnings, we can continue. So the next thing we're going to do is go to File, New, select the Block Diagram / Schematic File option, and double-click the white space. On the project, hit the drop-down. There's a symbol for what we just created. There's a symbol. So when we said create update symbol file, we were creating a symbol that's going to display the inputs and the outputs for the code we just wrote. Now, if you double click that symbol file, you see the code that's behind it. It goes right back to the code we wrote. So now that we have a symbol file, the next thing that we're going to have to do is add inputs and outputs. So we're going to go to this menu right up here, select the drop down and click input. Add 3 inputs to your diagram. Add 2 outputs. And we're going to connect each one of these directly to each input that you see on the screen. Same thing for the outputs. All right, so we've got those connected. Now each one of these is eventually going to represent a certain pin or a certain location on your PLD. Right, now we're going to give each one of these a name. I'm going to call this in_A because it's an input. It's input A. That's going to be in B, in C. If you hit enter, it'll automatically drop you down to the next one. So click it until you get the gray box, start typing, hit enter, and you go to the next one. On the other side, I'm going to call this one out_X and out_Y. Now this file right here is what we're going to save as our top level schematic. The top level schematic is like the file that has the most priority or precedence within your work. The top level schematic has our symbol for our combinational logic function. It defines our inputs and our outputs. This is the file that you're going to save with the exact same name as your project. It must be this file right here. So it's going to give you that by default, and you're going to hit save. And now we're going to compile this entire project. So we're going to hit this blue play button up here to start the compilation. And it usually takes anywhere from 2 to 4 minutes. You're going to see a lot of messages and things pop up down here on the screen. As long as you have warnings and no errors, you're okay. If you see an error, that'll come up in red, and that means that something is wrong and you have to go back and fix it. So we're going to let this compile for a few minutes. Once we're done, the next thing that we're going to do is functionally simulate our work. So that means we're going to make sure that our logic is completely spot on before we actually program it onto the PLD. So we're going to wait for that compilation to finish. You can actually see how far along you are in the process by looking in this window right here. So there's a couple of steps before you get to the final step. And you're just going to wait for that to complete. Again, don't worry about warnings. Warnings are okay, errors are not okay. So we can see we're at 98%, okay, and it says at the bottom, Quartus Prime full compilation was successful, 0 errors, 15 warnings. So it compiled, it's successful. And now we're ready to simulate our work. So to do that, we're going to start by making sure the path for our simulation tool is correct. So we're going to go to Tools, Options, EDA tool options. And we're going to look at the Multisim Altera path, which is the one at the bottom of your screen. And you should have a path that maps to this folder right here. If you installed the Quartus software directly to your C drive, this should be the path that you see right here. If you don't see this path, take a pause and navigate to it. If you did not install Quartus directly to your C drive, navigate to where you did install Quartus, and then from there, within those folders, look for the Intel FPGA_Lite folder, 18.1, and so on. This is the path you should see to navigate to the simulation tool we need to use. So make sure that you have that there, and then once you do, hit OK. All right, now we're going to go to File, New. At the bottom, scroll down, University Program VWF. We're going to open that up. This is going to allow us to get a waveform to simulate our code. So the first thing that we're going to do is go to Edit, Insert Node or Bus, click the Node Finder button, click List, and right there are the inputs and outputs that we added to that PDF file with the names we typed out. That's why we have to name everything so we know what it is, and we can see that it's an input or an output. So we're going to go ahead and add all of these by clicking the double arrow to the right to our waveform. So hit OK twice. We have input A, input B, input C, output X, and output Y. Now we have to tell this simulation tool what input A, input B, and input C are going to be. We're going to run the simulation, and then it will tell us what output X and output Y are going to be based on the code we wrote. So this is how we're going to verify that our code works the way it should. So we're going to start setting this up by going to Edit, Set and Time. We're going to make it 16 microseconds. 16 microseconds. Hit OK. All right. Select in A, and then on your keyboard, hit Control-Alt-K. That's a hotkey. We're going to give a period to this waveform. We're going to make that period 8 microseconds. And you'll notice on the screen, A has now become square wave with a period of 8 microseconds. Select input B and hit Control-Alt-K. We're going to make this one have a period of 4 microseconds. And this one will have a period of 2 microseconds. Why did I pick it that way? Let's look at A, B, and C as we go from the left to the right. 0, 0, 0, 0, 0, 1, 0, 1, 0, 0, 1, 1, 1, 0, 0, 1, 0, 1, 1, 1, 0, 1, 1, 1, start over. It's counting from 0 to 7, or it's walking through your truth table from 0, 0, 0 all the way down to 1, 1, 1. This is how we set up those inputs so that we can test out our logic and make sure that X is high when it should be and that Y is high when it should be based off of our logic. So now that we have our input set up, we're going to have to run the simulation to have it tell us what output X and output Y are based on our inputs. So to do that, you're going to go up to this button right here and hit Run Functional Simulation. It's going to ask you if you want to save your changes. Just click Yes. You don't have to change the name unless you want to. You don't have to change the default position of where it's going to save unless you want to. Just hit Save. You're going to see the simulation flow progress window up on your screen. Just let that run. And when it's done, a new waveform will pop up on your screen. Notice that A, B, and C are exactly as we designed them to be, and now we can see output X and output Y. Let's go through and compare output X and output Y to our truth table on the first page of the laboratory exercise. So when A, B, and C are 0, 0, 0, X should be 0 and Y should be 1. Correct. When A, B, and C are 0, 0, 1, X should be 1, Y should be 0. Correct. When we have 0, 1, 0, Y should be 1. X should be 1 and Y should be 0. Correct. When we have 0, 1, 1, that's right here, 0, 1, 1, they both should be low. X is low, Y is low. When we have 1, 0, 0, X should be high, Y should be 0. When we have 1, 0, 1, X should be low, Y should be high. When we have 1, 1, 0, x should be low, y should be high. And when we have 1, 1, 1, x should be 1, while y is low. So this functional simulation verifies that the code we wrote works the way it should based off of the problem statement. Our code has been simulated right here. Based on the simulation, we can expect x to be high and y to be high based on the values of a, b, and c, and it matches our truth table exactly. So this functional simulation is a way to double check and make sure that your code works the way you intended it to. Now that we've double checked that, we're ready to actually put this on the PLD and verify that it works on the PLD. So we're done with this waveform. You can close it. And we're going to go back to Quartus. All right, so we're going to go back to our BDF file. Now that we have compiled the design, we functionally simulated it, we're going to program the PLD. In order to do that, we have to specifically state what pin on our circuit board, on our PLD, is going to correspond to input A, input B, and input C. So in order to assign the pins, we need to refer to the DE10 Lite user manual. This has been posted on Canvas. It tells you all of the information about the PLD itself. So if I wanted to access a push button, key 0 or key 1, I have to reference this pin number right here in Quartus. If I want to use a switch, here are my switches. If I want to use any one of these switches, I have to reference a certain pin number in Quartus. I also have to declare the I/O standard in Quartus. So for this assignment, we're going to use switch 9 for input A. So that means I have to reference pin F15. We're going to use switch 8 for input B, so I'm going to have to reference pin B14. And I'm going to use switch 7 for input C, so I'm going to have to reference pin A14. So for my switches, I have to go to this user manual and figure out what pin do I need to reference in order to use that switch. Same thing for the LEDs. In order to use a specific LED, I have to know what pin number I'm going to reference. So for this assignment, I'm going to reference LEDR1, which is right here. LEDR1 I'm going to use for output X, and LEDR0 I'm going to use for output Y. So those are the pins I'm going to be referencing in Quartus. So I'm going to go to Assignments, Pin Planner, and I have to enter those pins. So for each input, I have to enter those pins from the user manual. So for input A is going to be switch 9. Which is going to be pin F15. So I'm going to go to the location column and type in those pin numbers to correspond to my inputs and outputs. I want switch 8 for input B, so I'm going to do pin B14. Remember, I'm getting each one of these pins from the user manual. Input C is going to be switch 7, which is pin A14. And for my outputs, pin A9 is going to be LED1. I'm going to assign that to X. And then pin A8 is going to be LED0. I'm going to assign that to Y. The other thing that we need to do is make sure that the I/O standard is this option right here for every single pin. 3.3-VLVTTL. So make sure you open up the drop down, or you can start by typing in 3.3 and then scrolling down. But each one of these should say the 3.3 VTTL. This will automatically save as you type in your work, so you don't have to hit save, just close it. Notice that the pin assignments we just made are on the screen. There's my pins. So now, anytime I want to use input A, I'm going to manipulate pin F15, which is switch 9 on my board. So we have switch 9, switch 8, switch 7, LED 1, and LED 0. Now that I've assigned the pins, I'm going to compile again. While it's compiling, now's the time to go ahead and get your PLD out and connect it to your computer using the USB cord. Remember, you must have the USB blaster installed in order for this to communicate with your computer. So while you're waiting for it to compile, get that out, plug it in. You'll notice when you plug it in that a default program is always going to run where it just scrolls through numbers on the hex display. That's always going to be the startup program until you program the PLD. So right now we've got it plugged in and we are waiting for the compilation to finish. You're always going to have to do that second compilation after you add the pin numbers. All right, and we have an error. Somehow my output Y, I must have grazed the keyboard when I typed that in, it didn't save. So see, I got an error. If I don't assign these with the right IO standard, you'll get an error. So I fixed that. I'm going to close it. And I'm going to hit compile again. Be prepared to get lots of error messages as you're learning how to do this. Also be prepared to have to figure out how to fix those errors on your own by researching them, Googling them, read through the book, look at your syntax, review the videos and make sure you've aligned everything according to the videos. But sometimes an error will take time to fix. It may not be a quick fix. Be prepared for that, especially when you're new to programming. So right now we're just going to wait until it finishes compiling. All right, our compilation was successful. Now that the compilation is complete, we're going to go in this window and scroll down and go to Program Device. Double click that. A new window will open. Now, if you've already installed the USB blaster, this should automatically detect your device right here. If not, you're going to have to add the device. Make sure that your hardware setup says USB blaster. If it doesn't, you can click that button and select USB blaster. Make sure it says USB blaster up here. Make sure the mode here says JTAG. Make sure you can see this image with your device number shown right here, and there should be a file listed right here. This is your configuration file that is going to be downloaded to the PLD. So you have all of this set up, ready to go. You're going to hit start. Sometimes you get a fail the first time. I get this all the time. Usually try it 2 or 3 times before you decide that something is wrong. So hit start again. And it's successful. So I often get a fail the first time if I haven't connected my PLD to the computer for a while, if it's been a minute, which it has in my case. So if you hit start once, don't worry, hit start again. You should see at the top the progress, 100% successful. And if you see that button, your program is currently running on your PLD right now. So what I want you to do is manipulate the switches and watch the LEDs change. Remember, switch 9 is input A, switch 8 is input B, switch 7 is input C, LEDR1 is output X, LEDR0 is output Y. So you're going to manipulate those switches and make sure that your code is working correctly on the PLD. Alright, so at this point, if you go back to the problem statement, you can see that we successfully created a design description in VHDL for the truth table given. You should be able to see that as you manipulate your 3 switches, the lights go on and off based on the values for X and Y given in the truth table. If you're not seeing that, you may have run into an issue. Feel free to reach out to a lab assistant or shoot me an email if it's not working the way that it is supposed to. If you have any questions on this video or any steps of the programming process, feel free to shoot me an email and I will respond as best I can. That sums up our introduction to VHDL design. Next week, we're going to start digging into the VHDL code system and understand a lot of the functionality and options you have when writing code for a hardware like this particular PLD. And as we go throughout the semester, we're going to revisit many of the devices you've already learned about, like counters, memory, encoders, decoders, multiplexers, etc. And we're going to learn how to write all of those in VHDL and then program them onto the PLD. And that is the end of this video.